let's take a look at an example in which we have a light ray entering a rectangular prism, okay? I think it's going to be really advantageous if you draw this prism out on your paper, and I really suggest that you draw it big. I'm talking about half a page, because if you draw it too small, there's going to be so many angles going on in this little space here. If you draw it too small, you just can't fit all that in a little space. So I strongly recommend that you draw a nice big representation of this rectangular prism here. This is going to be an acrylic glass prism, which is like a plastic glass, and the index of refraction is about 1.4, and the light ray will be coming from the air, so air into this acrylic glass, okay? So what you can see in this diagram is that we have the light ray coming in red here. The incident angle theta 1 is 80 degrees to the normal. Notice that we've drawn the normal as a dotted line right here. And what we want to do is we want to trace this ray through the prism. The question is, how does the ray exit the prism? Let's start out with Snell's law. We know that when we go from a low index of refraction into a high index of refraction, the light ray bends towards the normal. So if this is the light ray here, it's not going to bend away from the normal, it's going to bend toward the normal. So we're going to take this light ray right here, we're going to bend a little bit toward the normal like this. Okay? So hopefully you have a straight edge or a ruler, and you can draw this refracted ray toward the normal. Okay, so notice that it bent toward the normal as you see over here. Okay? So now notice we have a new boundary between the acrylic glass and the air again. So what do we do where this light ray meets the boundary? We have to draw another normal. So I'm going to go ahead and I'm going to draw another normal over here where the light ray meets the boundary. And the question is, going from the glass into the air, we're going from high index of refraction into low index of refraction, what's the light ray going to do? And of course the answer is it's going to bend away from the normal, right? So let's go ahead and let's draw this light ray bending away from the normal like so. Okay? So we want to label this angle over here theta. This is what we're solving for. Okay? Now, in between the incident ray and the exit ray, there were a bunch of other angles that we want to explore. Okay? The first thing that I want to label is, if this is theta 1, then theta 2 will be this angle over here. It's absolutely important that we label this angle theta 2. Okay? Then the light ray enters this boundary up here, and this is another theta we have to keep an eye on. We're going to call this angle here theta 3. Okay? And then when the light ray passes into the air again, we're going to call this angle theta 4. And this angle ultimately is what we're solving for. Okay? So we're going to apply Snell's law a couple of times here. First, we're going to try to find theta 2. Okay? So our first order of business is to find theta 2. Okay, so find theta 2. Okay, so we're going to use Snell's law. We're going to say, okay, sine of theta 1 times n1 equals n2 times sine theta 2. Okay, let's plug in our numbers. So n1 is 1, that's the index of refraction of air, times the sine of 80 degrees equals n2 is 1.4 times the sine of theta 2. And if you solve this for theta 2, you're going to get theta 2 is equal to the sine inverse of sine 80 divided by 1.4. And I hope you see what I did there. I just divided both sides by 1.4 and then took the sine inverse of both sides to get theta 2 by itself. And if you calculate this theta 2, you're going to get 44, or I should say 45. Oh, I was looking at the wrong paper. We're going to get 44, that's correct, 0.70 degrees. We're going to carry it out to 4 sig figs, just because with sine functions, you want to be really careful with sig figs because a little bit of difference with sig figs can affect your answer a lot. So we got 4 sig figs there for our theta 2. All right, good deal. Now we want to find theta 3. Okay, so take a look at this picture here and ask yourself, with your geometry skills, can you solve for theta 3? my hint to you is to carry out these normal dotted lines a little bit further. Okay? Carry this one out a little bit further as well. Where this normal meets this normal, what kind of angle do we have in there? If you said that that was a right angle, you're 100% correct. Why is that? Because this is a rectangular prism, which means that this side is perpendicular to this side, which means that this normal is going to be perpendicular to this normal. All right? So the question is, if you have a right triangle represented in here, what's got to be true about theta 2 and theta 3? In a right triangle, the two acute angles always have to add up to 90 degrees, right? Because this is already 90 right there, and the sum of all angles in a triangle has to be 180 degrees. So theta 3 has to be 90 degrees minus 44.70 degrees, or 45.30 degrees. Okay? So we just found theta 3. Fantastic. Let's go ahead now and try to find theta 4. So what are we going to do? We're going to apply Snell's law again. Okay? So let me use a different color here. Okay? To find theta 4 now, we're going to apply Snell's law. So let's call the index of refraction associated with theta 3, let's call it N3. So we're going to say N3, this is going to be the index of refraction associated with theta 3, which of course is just the acrylic glass, 1.4, times the sine of theta 3 is going to equal N4, that's going to be the index of refraction associated with theta 4, times the sine of theta 4. Okay? So now what we want to do is solve for this theta 4. So let's plug in what we know. The index of refraction associated with angle 3 is 1.4, so this is going to be 1.4 times the sine of theta 3, which we just proved was 45.30 degrees, equals N4, the index of refraction associated with theta 4 is just 1. So this is just 1 times sine of theta 4. Alright, and if you solve this for theta 4, all you have to do is take the sine inverse of both sides, and we can do that up here. So I'm going to give myself a little bit more room, and I'm going to say, okay, theta 4 is going to be equal to the sine inverse of this expression here. So 1.4 sine of 45.3 degrees. Alright, I kind of ran out of room there, but we can calculate sine inverse of 1.4 times sine of 45.3, and you're going to get theta 4 is equal to, we're going to get 84.3 degrees, which is consistent with our diagram, right? Based on how we drew our ray, this angle right here, very plausibly, is 84.3 degrees. So we feel good about that. And that is the final answer. Okay? Now, this would just be part A of a question. What about part B? Let's take a look. So part B might look like this. It might say, find the incident angle theta 1 at which the light ray exits at 90 degrees to the normal. Now, if we look back at our diagram here, okay, if we look back at our diagram, we see that this light ray up here exited pretty close to perpendicular to the normal. Okay? The question is, what would this angle theta 1 have to be such that we were on the verge of total internal reflection? Remember, when this angle is 90 degrees, we're almost at total internal reflection within this prism. So the question is, at what angle are we just about to achieve total internal reflection? So this angle we want to set to 90 degrees. Okay? So our strategy here, is going to be, well, let's redraw our diagram really quick. So we have our rectangular prism here, like so. Okay? We know that our exit ray, we want to be perpendicular to the normal. So here's our exit ray right here. The normal, of course, is our dotted line right here. We want this theta 4 to be a 90 degree angle. We want theta 4 to be equal to 90 degrees. Okay? So in order to achieve that, we know that the light has to come in at some angle. We're going to call this angle theta 3. And we know that there has to be another normal over here. And associated with theta 3, there's going to be a related angle, theta 2, over here. And then finally, coming in over here, there's going to have to be a theta 1. And this is ultimately what we want to solve for. So notice that our strategy here, is to work backwards. So whereas in part A of this problem, we started with theta 1, we worked our way to theta 4, and now we're going to start at theta 4 and work our way backwards to theta 1. All right? So let's start by looking at theta 4 and trying to get theta 3. We know that the index of refraction of this acrylic glass is 1.4. We know the index of refraction of the air is 1.0. Okay? So let's set up our favorite equation for refraction, which of course is Snell's law. So we're going to say n3 sine of theta 3 is going to equal n4 sine of theta 4. Okay? So n3 associated with angle 3, that's going to be a 1.4. Sine of theta 3, that's what we're solving for, is equal to n4. So the index of refraction associated with theta 4 is equal to 1 times sine of theta 4, sine of 90 degrees. And ask yourself, what is the sine of 90 degrees? Obviously, this is just 1. Okay, so 1 times 1 is 1. So when we solve for theta 3, we're going to get theta 3 is equal to, so we divide both sides by 1.4. So we're going to get 1 over 1.4 over here. Then we have to get rid of the sine function by taking the sine inverse of both sides. And if you solve for this theta 3, you will get none other than 45.58 degrees. Alright, so we found theta 3. Now we got to find theta 2. And if you remember back to part A, we looked at this and we said, hey, this is going to be a right triangle. And the two angles of a right triangle, the two acute angles, have to add up to 90 degrees. So therefore theta 2 has to be 90 degrees minus 45.58 degrees, which is going to be equal to 44.42 degrees. So we just found theta 2. And all that's remaining is to try to solve for this theta 1. So we're going to apply Snell's law one more time. We're going to say, okay, n1, and I'm going to work a little bit on this side over here. Okay, we're going to say n1 sine theta 1 equals n2 sine theta 2. n1, so the index of refraction associated with theta 1 is going to be 1 times sine theta 1, well, that's what we're solving for, is equal to the index of refraction associated with theta 2, which is 1.4, sine of theta 2. Well, we just found theta 2 is 44.42 degrees. Okay, so now if you want to find theta 1, you take the sine inverse of both sides. So sine inverse of 1.4 sine of 44.42 degrees. All right, and if you calculate that, so sine inverse of 1.4 times sine of 44.42 degrees, you're going to get a theta 1 of 78.49 degrees. Okay, so this angle over here is 78.49 degrees. And what that means is, if we were to, let's say, decrease theta 1 at all, if we were to make this ray come in at a little bit of a smaller angle, that means we would have achieved total internal reflection over here. And none of this would pass through the barrier at all. It would all reflect internally. All right? So those are the strategies that we use when we work with rectangular prisms. Okay? In the next video, we're going to take a look at how we work with triangular prisms. All right? Thanks for watching.